Today we will discuss about micromechanics system design. This is a part of module 2 under this microrobotics course. In this micromechanical system design, so we will be discussing about the micromechanic systems, micromechanical analysis with reference to static condition, the energy methods for elastic beams with reference to dynamic conditions, design and selection of material for microrobotic systems, control of surface worker. So these are some kind of basic fundamental which will be helpful for us to understand the available micro robotic system as well as to design the micro robotic system based on the requirement. Let us start with a simple case study. So in this particular case study, the main motto is to establish a biomimicking robot, establish a biomimicking micromanipulation robot which is in the form of a caterpillar form. So basically we are trying to biomimic a caterpillar motion. So if you closely observe the movement of this caterpillar, so this caterpillar motion is called as two anchor crawling motion. So why it is called as two anchor crawling motion? Because, so let us consider there are two legs are there. So this is position 1 and this is position 2. So for the locomotion, ideally first the position 2, that is the leg 2, will try to anchor it and then it will try to pull the leg 1 towards leg 2. So like this, by sequencing this particular operation throughout, a locomotion is exhibited over here. So in this particular locomotion, so we can also manipulate it on a micron level. In certain cases, we can also manipulate it on a macro level. However, since our main motto is for a micron level, so we may need to closely observe the different mechanisms which are involved in it. So when we try to use this mechanism, this has a potential application in kind of a micro manipulation in electronic industry. It also has a potential application towards surveillance applications. It also has a potential applications in handling some of the delicate component, moving in a delicate component, etc. So for this, for exhibiting this particular micro mechanism or for demonstrating this particular micro mechanism, so we have taken a small PLA material. So this PLA material was baked in such a way that this PLA material becomes flexible. Over the PLA material, so we have bounded the shape memory alloy structure. So these shape memory alloy structures will be actuated using a kind of a joule heating by applying an electrical pulse to it. So in this particular case, so while programming our shape memory alloy and while we were integrating the shape memory alloy in these PLA structures, what we could observe is we could establish two different type of locomotion. So one locomotion is something like this, like if there is a kind of structure over here and when we try to wound a shape memory alloy structure in this, by actuating the shape memory alloy appropriately, there will be a kind of a diametrically increase and decrease in the structure. This diametrically change in the structure will be helpful for us for a forward locomotion. So that is, once this diameter gets reduced and once this diameter gets increased, appropriately we get a positive direction. Similarly, once this diameter gets decreased and once this diameter gets increased, we get a negative direction. So such kind of locomotion, which we call it as a kind of a peristaltic locomotion. In addition to this, one more locomotion which we also call it as a single stair arrangement. So in the single stair arrangement as shown over here, so what we had performed is like it is almost equivalent to a two anchor crawling system. So in this two anchor crawling system, so one end of the shape memory alloy is fixed over here and the other end of the shape memory alloy is fixed over here. By actuating it, you get a positive and a negative displacement. That is, by actuating it, we get a kind of a compression in the spring, which is leading to a kind of a compression in the entire PLA structure. And when the PLA structure is in such a way that inside we will be having a kind of a single end spring, so that this single end springs will be capable enough in such a way that these are called as self-energized spring. So these self-energized spring will try to pull back so that we can create a kind of peristaltic locomotion what we are looking for. Now in this particular case, on an experimental perspective point of view, so we had performed the experiments and we could establish the locomotion. However, there is a need to understand the physics behind this and the design behind this. So in order to understand the micromechanism behind this, so this particular course content will focus on some of the key fundamentals related to micromechanics. So the first micromechanics which we will be discussing about is related to a micro robot which is considering both rigid and a flexible deformation. So when micro robots uses both rigid and flexible deformation of the element to achieve a desired motion, the element can be of different shape such as rod, beam, membrane, plate, shells, etc. Now as far as in this particular case is concerned, a rigid motion versus deformable motion in a solids, microsystems have both types. Like as far as in this particular case, in a rigid body motion, no relative motion occurs between points as in the movement of block above and rotation of the crank below. However, in the case of B, we have a relative motion between the points when bar stretches above or a bar bends below. Now, let us consider a bar with a static state that it can stretch or contract without bending. So, the bar is considered fixed at one end and load is applied on the other end. So in this particular case, we are considering two different conditions. In first condition, a bar is under single load and internal force P is same throughout the bar. And in another condition, where bar is under two load, so the internal force is different sections of the bar. So the stress acting through the length of the bar is represented as sigma equals P by A. So in this case, for uniform sections of the bar, the stress is same throughout. For varying cross section of the bar, the stress varies throughout the applied load is same throughout. For example, the conical or a pyramidal tip of an atomic force microscope. So in the case of a pyramidal tip, so we have a kind of a stress which is same throughout, whereas in the case of a conical tip, we have a focused applied load which exhibits over here. Now, when I talk about the micromechanics perspective point of view, let me just introduce you to some of the basic concepts. One is strain is the ratio of change in length to the original wrench, which is represented as epsilon, that is equals del L by L, which basically corresponds to change in length by original length. And stress and strain are related to the Hooke's law, which is represented as sigma equals E epsilon, where E is the proportionality constant called as Young's modulus, which is for both contraction and expansion. Now, considering the equation of the earlier sigma, when we try to equate it, P by A equals E del L by L. Thus, del L equals PL by AE. Now, let us consider this is a kind of a generalized equation which is considered for a simple system. Now, let us consider a micromechanics of a thermal stresses. Consider a bar fixed at both ends and heated uniformly to a temperature del T above its original temperature. The thermal strain and stress developed due to ceasing the thermal expansion of the bar is given as epsilon equals minus alpha del TL by L, which is minus alpha del T, and sigma equals E epsilon, which is nothing but minus E alpha del T. For example, a micromachine resistor fixed at both ends is supplied with the voltage difference across it. So this is a kind of a structure which is being suspended between the two anchors. Similarly, when we try to consider a kind of a transformably deformable element or beam, this is a kind of a load is applied in a transverse direction of the length of the beam, which deforms the beam in transverse direction. So the deformation is calculated using a beam theory. So in order to calculate the deformation, let us consider a beam under a tip load F is the transverse direction. So let us take an example of a simple micro machined accelerometer. So, this is an example of a simple micro machined accelerometer. So, in this accelerometer, if I try to introduce, we have a mass in place, then there are two anchors which are available, and then there are two suspension beams which are available. Now, if we closely observe in this, so in this schematic, a micro machined accelerator with the mass of 4 suspension beams and anchors are there. Now, deformation of the beam is due to axial force and acceleration in x direction, and vertical motion of mass is due to acceleration in the y direction. So, with reference to x direction, it is represented as del x. So, if the acceleration acts in x direction ax, each beam deforms axially and we can calculate the displacement of the mass. So, the beam will act as a rigid bar. All the beam will have same absolute magnitude of deflection. If acceleration acts in y direction, we term it as ay, which is represented over here. The bending deformation is called as y direction. Additionally, a vertical shear force will act along the z direction. Now, the micromechanics of this particular aspect is concerned. The axial force is shared equally by all springs. Thus, the deflection of the spring is given as del x equals max by 4 Ka. So, Ka is the axial spring constant. Similarly, when we try to calculate the equivalent spring constant, it can be represented as Kx equals 4 Ka, which is nothing but max by del x. So, now when we try to consider this, the deflection of mass with acceleration in x direction only. So, the 4 bars, so which can be represented as F equals, and the 4 bar connected to the mass can be considered as spring in parallel. So, the axial force generated due to the acceleration of the mass can be represented as F equals max, where m is the mass, ax is the acceleration in x direction, and the axial spring constant can be considered as k equals F by del x, which is nothing but PAE by PL, which is AY by L. Now, let us take a deflection of mass with acceleration in y direction. So, in this case, acceleration AY is acting in y direction. So, the 4 beam which we had mentioned over here, which is nothing but the 6C configuration, acts as a spring and share the force MAY equally. So, primarily the deforming bending due to MAY is considered as V, and the secondary deformation shear force is considered as F. So, at any section of the beam, the bending moment can be considered as M equals V x minus L, that is equals F x minus L. So, in this particular case, if we try to nomenclate it, so we have a kind of a cantilever beam with tip T and the shear force V and the bending moment M. So, during bending, there is a line within the beam where the beam neither expands nor contracts, and this section is called as the neutral axis. Now, when we try to look into this, which is called as a neutral axis of the plane or the axis. Now, let us take one more example, or it is called as a, like we can use a kind of a, since we are discussing about the bending moment in the system, so let me just discuss you with one important case study. So in this case study, so what we are trying to explain is, so we were involved in establishing a kind of a jellyfish kind of structure. So the main focus involved in jellyfish kind of structure is, so in order to fabricate this jellyfish kind of structure, what we did is, so we had a kind of a small Kapton polyimide. So in this Kapton polyimide, so we have integrated a shape memory alloy structure. So in this shape memory alloy structure, so that we are trying to actuate the shape memory alloy structure in such a way that there is going to be a kind of a bending, that is a kind of a actuation and a deactuation which happens, which will result in a kind of a bending in this particular system. Now, in order to ensure the kind of a static, or in order to ensure a kind of a dynamic analysis in this particular system, so what we have done is, so this is a kind of a Kapton polyimide. So in this Kapton polyimide, to take care of the retraction, so a rubber string is established. However, in order to take care of the actuation, the SMA integrated polyimide was established. So when we try to, so in this SMA integrated polyimide, so what we did is, so we had a polyimide, so there were small holes were drilled using a laser, and the SMA wires were strained up to 2%, and these strained SMA wires were integrated with these polyimide structures, so that there is going to be an actuation in this SMA, and then there is going to be a deflection in the polyimide structures. So what we are trying to do is, so we are trying to integrate these strained SMA wires inside these Kapton polyimide structures, and these Kapton polyimide structures are well encapsulated using a kind of a Kapton type which will be integrated into the system. Now what we are trying to do is, so this become a kind of an integrated structure with a Kapton tape and a Kapton polyimide which is available, and this integrated structure is fixed into the rubber material. Since already 2 to 3% strain is induced into it, one way of actuation is taken care by the shape memory alloy, and the return stroke is taken care by the Kapton polyimide which is available over here. So the main function of this Kapton polyimide is, the return stroke is taken care and the positive actuation stroke is taken care by the shape memory alloy. However, in order to support the Kapton polyimide, an additional rubber string were also connected to this Kapton polyimide in such a way that there is a kind of an actuation which exists. So through this actuation, we can have a continuous pulling of this particular SMA structure, which will result in a kind of a bending in both the directions. So that is, let us consider if there is a cantilever structure which is available over here, and then there is an SMA integrated with a wire. So what happens is, by actuating it, we can have a kind of a continuous actuation. In fact, we can have a control over the frequency. So in this particular case, so one of the important aspect is, let us consider each tentacle of this particular SMA based jellyfish structure is considered, and these jellyfish structure, the deflection in these jellyfish structures were completely found in such a way that completely analyzed in such a way that each and every jellyfish structure is tentacles of the structure is considered as a cantilever, and with reference to the cantilever the deflections were studied. Now, so one important aspect is, so like since there is going to be a kind of a change in the expansion and contraction, the expansion and the contraction needs to be appropriately studied, and it needs to be modeled to study the overall waviness, because frequency has a direct impact towards the swimming capability. Now, so we have done a kind of a kinematic modeling to the system. So in this kinematic modeling, so what we have done is, so we have integrated the SMA based structure, and then so we have also performed a kind of a operation which exhibits in such a way that, like, we can study the waviness and we can also study the kinematic analysis of the system. Now, in this particular case, if we closely observe, two important aspects comes into the picture. One is a kind of a neutral axis which exhibits, other one is a kind of a curvature or the waviness which we may need to study in detail. Now, with reference to this neutral axis, so if you try to see, so this is a kind of an actual jellyfish kind of structure which is model, and this is a kind of a prototype jellyfish structure, so which we are trying to mimic to create the kind of a motion similar to the actual jellyfish. So, now in this particular case, so there is a need to understand the neutral axis, and there is also need to understand the overall curvature and the waviness which exhibits over here. So in this particular case, so when we try to closely observe, so there is a need to understand the axial strain. So let us consider this beam as a pure bending beam. So the axial strain in the beam is considered as epsilon x equals p minus y theta minus p theta by p theta equals minus y by p. So epsilon equals c by p. Similarly, so when we try to talk about the axial stress is sigma x equals minus y sigma max by c. Okay. So here p corresponds to the overall length and the theta corresponds to the overall angle which is getting generated, and then there is a y parameter which exhibits over here. So the main function of y parameter will take care of the overall bending characteristics in this particular system. Now the deflection of the beam is, which ends loads F is given by del equal FLQ by 3E, and the slope of the loading tip is given as d dwell equals dx equal dl by d del by dx equals FL squared by 2EI, where I is the moment of inertia of the